So I'm sharing my screen now. Is the screen visible to you? Are you looking at my screen?
Yes, sir.
Right. So let us quickly see what we have discussed so far. So we started the discussion on defining groups and fields. Okay, and after that, so field is an extension of group, and using field we have defined vector space. And in vector space, elements of the vector space we call it as vectors only, and elements of the fields we are calling it as scalars. And every vector space is associated with a field f. So v means v over a field f. If the field is a set of real numbers, if the field of real numbers, then we call that as a real vector space. If the vector space is over a set of complex numbers, we will call it as a complex vector space. And we discussed about linear combination of vectors. If you have u1, u2, u3, then the linear combination is about c1 u1 plus c2 u2 plus c3 u3, where c1, c2, c3 are scalars. That means they are the elements of the field. And we also talked about spanning of a set of vectors. Okay, so if you take some set of vectors like u1, u2, and so on un, you take all possible linear combinations of those n vectors, then you will get a set which is called the span of the set, or the span or the linear span generated by the set of vectors u1, u2, and so on un. And we also talked about subspace. Okay, subspace is nothing but a subset of the vector space, which is itself is a vector space. And the necessary and sufficient condition for a subset of a vector space is said to be subspace is you take any two elements of the set. If the linear combination is also an element of the same set, then the set is going to be a subspace of the given vector space. And whatever the linear span we discussed earlier, okay, you if you are getting a set, if you are getting a set which is a linear span of u1, u2, and so on un, that itself is going to form a subspace of a vector space. Okay, so if any linear span of vectors forms a subspace, and that is the smallest subset of the vector space which contains a given set of vectors u1, u2, and so on un, I said. And after that we have seen some examples of linear spans, and after that we discussed about linear dependence and independence. Okay, and if you can rewrite one vector as a linear combination of the remaining vectors, then all those vectors are said to be linearly dependent, otherwise they are said to be linearly independent, I said. And we have seen some examples of linear dependence and independence, and we have seen how to identify whether a given set of vectors are linearly dependent or not. That is by finding the rank, right? So you put those vectors as a rows or columns of a matrix, and you convert into echelon form. Okay, if the rank is reducing in compared to the number of given vectors, then that is they're going to be linearly dependent, or the number of non-zero rows uh, in the echelon form of the matrix is going to generate the space generated by the given set of vectors, I said. And after that we talked about basis and dimensions. And basis is nothing but a set of linearly independent vectors which spans the given vector space. Okay, so basis has two qualities. The elements of the basis forms a linearly independent set, and the span of that set is going to be the entire vector space. Such a set is said to be basis, I said. And basis can be finite set or infinite set. If the basis is finite set, then we say V is said to be finite dimensional vector space. If basis is having n elements, we say dimension of the vector space is n. And if basis is having infinite number of elements, I said V is going to be called as the infinite dimensional vector space. And we have seen different examples of finite dimensional vector space as well as infinite dimensional vector space. So dimension is nothing but the number of elements of the basis, right? Or you can say the cardinality of the basis. Okay, is called the dimension of the vector space. And we have seen some theorems on basis, like basis is the largest linearly independent set, That means there is there is no superset of the basis which is linearly independent. If you add any one more element to the basis, that becomes automatically linearly dependent. And every subset of a linearly independent set is a linearly independent, and every superset of a linearly dependent set is a linearly dependent set. And if you see element 0 in the set, that automatically becomes a linearly dependent set. Okay, so and any two bases will have same number of elements. That means bases every all bases are having same number of elements. And also we said that a vector space can have different bases, but all bases will have same number of elements. And what we discussed, we also have seen how to find the basis of a vector space. Okay, or that is what I said. You put the vectors into rows and columns, and you convert into echelon form, and those rows are going to be the basis for the given vector space, and the number of non-zero rows are the number of non-zero columns. Okay, in the echelon form of the matrix. Okay, is going to form the dimension of the space generated by those vectors. Okay, and after that we have seen coordinates of a vector. And coordinates of a vector is nothing but like this. If a vector, if you are expressing as a linear combination of the given vectors for some coordinates, okay, then those coordinates put together is called the coordinate vector. Okay, so if you can express v as a linear combination of the given vectors like this, 3u1 plus 2u2 plus 3u3, then these three scalars 3 2 4, okay, put it in a row matrix form or column matrix form, are called matrix coordinate vector relative to the given vectors, okay, relative to the given basis. Okay, so when so that coordinate vector will change from basis to basis. I said with respect to the standard basis, this is a coordinate vector, and when you change the basis, okay, this is a coordinate vector. And how to find out the coordinate vector related to the given basis I have shown here. Okay, when given set of vectors are linearly independent and forming a basis, and if you want to express the coordinate vector of this vector relative to this basis, write this as a linear combination of the given vectors. This is actually u1 u2 u3. Then so that is what I have written here. Given vector I have written it as a linear combination of the three vectors here, and you equate the corresponding elements, you will get system of linear equations, that is a non-homogeneous system. Solve the system and find the solution. The solution will be for x, y, z, which we are looking at. That is going to form the coordinate vector. So we were at this stage. Am I right? So is it clear up to this concept? Do you want any clarification on the concepts that we have discussed so far? Also, we talked about row space and column space, right? The space generated by rows of a matrix is called a row space, and the space generated by the columns of the matrix is called column space. And we said row space dimension will be equal to the column space dimension. Therefore, in general, and row space dimension we call it as a row rank. Column space dimension we call it as a column rank. And rank of a matrix is nothing but the dimension of the row space or dimension of the column space. Okay, so shall we go to the next topic? Shall I proceed?
Yes.
Right, so next is about linear transformations. Okay, so so what is a linear transformation? First I'll use one note. See, transformation is nothing but a function. Okay, so function, what do you mean by function? You all know about a function. Function is a relation, right? Where each element of a set has a unique association with the an element of the other set. So if I have x, okay, it is uniquely associated with y. Uniquely associated with means what? This is not having any other association than y. Okay, like that every element of A should have that association with B. In that case, that kind of association or the relation, we'll call it as a function. So in general, f is a function from A to B. That is how we denote, right? So what is y called? Y called image of x under the mapping f. And what is x called? X called the pre-image of y.
Pre-image.
X is called the pre-image of y, and y is called the image of x under the mapping f. Okay, so how they are related means y equal to what? F of x. Okay. So what generally function means, we mostly will call function means f of x. But f of x is what? F of x is not the function. F is the function. F is the function. Can you see? And f of x is the general formula, mostly general formula for the image. Okay, in most of the cases we see general formula for the image as the uh, function, something like sin x. What is sin x? Sin x is the image of sine function, right? Sine is the function, sin x is the functional value. If you call this as f, okay, so what is f of x? F of x is nothing but sine of x, but sine of x we are simply writing it as sin x. Just we are removing the brackets. That means many times we, instead of writing f of x, we can simply write it as fx. Is that okay? So actual function is sine. Sin x is the functional value. Similarly, f of x is the image and f is the function. But most of the times we identify we identify we identify image formula with the uh, function. Is that clear? Shall I proceed?
Yes, sir. Yes,
Right.
sir.
Right. So now you can see matrix. Okay, so you have uh, a matrix of dimension, let us say uh, matrix sorry, matrix of order, you have a matrix of order n by 1. That means you can see this as an element of r dimensional space. Okay, that means x1, x2 and so on, xn. Okay. Similarly, suppose you have a matrix of order m by 1. That means you can see this as, sorry, not necessarily x. Call this as y. Okay. You can see this as an element of m dimensional space. Okay. So something like y1, y2, and so on, yn. Okay. Now you take a matrix A of order m by n. Of order m by n. Okay. So if I multiply this A with the matrix M, what is the resultant? A matrix of order m by 1, right?
Yes, sir.
Right. So that means what? This matrix is transforming a set of n dimensional vectors to a set of m dimensional vectors. Am I right? So that means you can see this matrix, okay, as a transformation, okay, or a function from the n dimensional space to n dimensional space, r power n, sorry, r power n to r power m. Like you have xn, you have ym, these two are related. How? By the matrix A. Okay, so that means how this function is defined. Actually, this is not A. I will tell you. This is actually let us say f. How f is defined? Or f related to the matrix A, is it? I will say, because I'm considering a matrix A. So let me call this as a function associated with a symbol A. So how I am defining uh, f a of f a of x, I'm denoting it as ax. Okay, if you are putting b, bx, if you are putting c, cx, like this. Okay, but as discussed earlier, most of the times, okay, we identify image, okay, with the function. So in that sense, you can see this as a function like fx, okay, or you can identify fa with a, okay. So that means we don't see much difference between, okay, interchangeably will be using the matrix and the function. Most of the cases, okay, in this kind of transformation, we identify the function fa with the matrix A, because basically this is the one which is transforming one matrix to another form, or one vector to another form. Okay, this basically a n dimensional vector, this is basically an m dimensional vector. Is that okay? So in general, you can have a mapping, okay, from a vector space of dimension n to a vector space of dimension u, like this. Okay, okay. So if you are taking v from this, if you are taking u from this, these two are associated like this. Like f is a function from a vector space v to another vector space u. Like f of v is equal to u. F of v equal to u. Okay. So you have such mappings, and this is an example of such mapping. Okay. So you know R power n is a vector space. R power m is also a vector space, and you are defining a function like this. Okay, f of fa of x equal to ax. So this itself, so matrix can be viewed as a transformation, matrix can be viewed as a function. So like that, there are several other functions which are defined from one vector space to another vector space. Is that okay? That another name for map transformation is called map. Okay, so f is a mapping from v to u. Okay, f is a mapping from v to u, or f is a mapping transformation from u to u. Shall I proceed?
Yes, sir.
Basically, transformation or map is nothing but a function. Okay, so now what is linear mapping? Okay, linear map or linear transformation. What is linear transformation? uh, Linear transformation is basically a mapping from f to u satisfying two conditions. Okay, first one is function of u plus v equal to function of u plus function of v. Second one is function of some alpha into u equal to alpha into function of u. That means what? It is preserving the property of operations in both the vector space. If I combine these two, I can say that f of c1 u1 plus c2 u2 is equal to, if you can write it as c1 f of u1 plus c2 f of u2. Okay, that means what? uh, u1 u2 are elements of u1 u2 are elements of v. Sorry, shall I change the operation notation? Because inputs I am calling it as v1, no? So if I am calling it as v1 and v2, so what it says, uh, f of linear combination of two vectors is the linear combination of the image of the two vectors. Okay, v1 v2 are elements of v, f of v1 and f of v2 are elements of u. Okay, so this is nothing but c1 u1 plus c2 u2. Okay, so if this addition operation and scalar multiplication is preserved, okay, then that function is said to be a linear function or a linear mapping or a linear transformation. Can you give some examples of linear transformations which are satisfying these two conditions are like this?
Matrices, sir.
See, basically it is a function. So how you are defining the function in terms of matrices? We have defined here, no? Can you see?
Yes.
Right, like that means if I can define f is a function from v to u, okay, by let us say this is of dimension n, let us say this is of dimension m, okay, f of v is equal to u, sorry, f of v equal to a into v. What is a into v? Becomes u, because it is m by n, as we discussed earlier, this is m by n matrix, this is n by 1 matrix, product is going to be m by 1 matrix. Okay, so what are the properties of this? Is this mapping satisfying these two conditions? You see, f of c1 v1 plus c2 v2. What is this? According to the definition, this is going to be a into whatever the input you are getting, that is going to be the a multiplied by that vector, right? So I will go to the next page. So if I am defining like this, f of f of v, f of v is equal to a into u. Okay, f is a mapping from n dimensional vector space to m dimensional vector. A is a matrix of order m by n. It's an n dimensional vector. This is an m dimensional vector. Okay, so so this is, sorry, every time I'm doing mistake. F a into v. Okay, so a into v is nothing but a into v. This is small v, sir. A into v. This is nothing but u. So what is f of v1 plus v2? F of v1 plus v2 is a into v1 plus v2 by the definition of this function. You know, matrix multiplication is distributive, therefore I can write it as av1 plus av2. So av1 is nothing but f of v1 plus f of v2. Similarly, what is f of alpha into v? So this is a into alpha v. So you can bring the scalar outside in a scalar multiplication or matrix multiplication, or a into v, and a into v. So a into v is nothing but f of v. Okay, therefore f is satisfying both the conditions, means f is a linear map. Okay, so the function how we are defining, okay, defines a linear transformation, and I am defining this function not by f, I am defining this function by fa, right? And that fa I am identifying with the matrix itself. Okay, so you can view every matrix as basically a linear transformation. Every matrix can be viewed as a linear transformation from an n-dimensional vector space, to m-dimensional vector space. Okay, so that means if I have a matrix of order 3 by 4, that means what? I have a that means this is a linear transformation which is transforming, which is giving a map from 4-dimensional to 3-dimensional. Is this clear to all of you? This can be viewed as a linear transformation from a 4-dimensional space to 3-dimensional space. Is that fine?
Yes, sir.
Right. Now, what? So, what are some properties of this? Okay. So, when I say space, let us assume that V is finite dimensional. Let us say V is finite dimensional. Let us say U is some vector space. U is some vector space. Now, do you remember range? Range of a function? What is range? Like this, no? What is A called?
Codomain.
A called domain, B called
Called codomain.
codomain. So what is range? Range is nothing but f of a. That means what? The set of all images. The set of all images of the function is called the range. Okay, so this is nothing but what? F of x such that x belongs to a. Right? The set of all images of the is said to be range, and you know range is always a subset of the codomain. Range need not be the codomain always. Range is a subset. Am I right? Now, what is an important property of this? What is an important property of this linear transformation? How when I say f is a linear transformation, what will be f of 0? Can you tell me? I'll take one more page. What is f of 0? Can I write f of 0 as f of 0 plus 0? 0 plus 0 is 0. Because 0 is additive identity. Am I right?
Yes, sir.
And when I say f is linear transformation, can I write f of 0 plus 0 as f of 0 plus f of 0?
Yes, sir.
Now when I say this is true, and you know f of 0 is nothing but f of 0 plus 0. Do you agree?
Yes, sir.
This is f is a function, linear function from v to u. This is the additive identity of v. Okay, and this is the additive identity of u. Both are we are denoting with 0. Do you agree? Because f of 0 is image. Image will be there in u. Input will be there in v. Inputs are from v. Outputs are from u. Okay. Now you see f of 0 plus 0 equal to, therefore f of 0 plus 0. I can write in reverse way also, because addition is commutative. You know, abelian group. Okay. F of 0 plus f of 0. That means what? When I apply cancellation law in a group, that means f of 0 equal to 0. F of 0 must be equal to f of 0 equal to 0. So what it says, when you have a linear transformation, what is the necessary condition? If you have a vector space to another vector space, a linear map, okay, then 0 must be necessarily mapped to 0. 0 must be necessarily mapped to f. Okay, if somebody gives a function, okay, and so what is the thing you see? First you put 0 in that function. Output must be 0. If you are not getting the output as 0, then f cannot be a linear transformation. F cannot be a linear transformation. Do you agree or not? Okay, so a linear transformation maps 0 element of v to 0 element of u. Do you agree?
Yes, sir.
Right. So that is one property. Okay, f of 0 equal to 0. What are the next properties? Okay, so not only it is not necessary that only 0 is mapping to 0. There may be some other elements also mapping to 0. Right? Collect all those elements of V which are mapping to 0. Okay, so that is called kernel of the function. Ker f, kernel. So what is the definition of kernel? Kernel is basically a subset of V. Can you see that? Kernel is a subset of V. What kind of subset it is? It is elements of V such that f of V equal to 0. Collect all those elements of V which are mapping to 0. that is said to be kernel of the transformation. Basically, this is a transformation, remember. Is this point clear to you? We will see some examples. Okay. Do you agree? Is this geometrically clear to you? What is kernel?
Sir, can you repeat?
Kernel is a set of elements of V which are mapped to 0. You collect the elements of V which are mapped to 0 in U. That collection is said to be the kernel.
Yes, sir.
Okay. So kernel is a subset of V whose elements are mapped to 0. Now every function will have a range, right? As we discussed earlier, every function will have a range. Okay. Obviously 0 is an element of range. So this range of f, this range is called image of f, which is nothing but range of f. Obviously we know range is a subset of U. So how these elements of so what are the range? What do you mean by range? Range is a collection of images. What is the image? Image is nothing but f of V such that V belongs to capital V. You collect all images of the function, that is said to be the image of the function. Are these two clear? Are these two definitions clear? Kernel f is a subset of V. Image f is a subset of U. Image f is nothing but the range. Okay, image f is nothing but the range. Okay. Now the interesting point is they are not only sets, they are actually spaces. Kernel f is a subspace of V. Subspace of V. And image f is a subspace of U. Okay. So how do you show that kernel f is a subspace? What is the condition to check a given set is vector subspace or not? If I want to check W is a subspace of V, what is the condition? Do you remember? E is a subspace. W is a subspace of V if and only if, okay, alpha 1 W1 plus alpha 2 W2, okay, must belong to alpha 1 W1 plus alpha 2 W2 must belong to the same set W. For all W1 W2 belongs to W, and for all alpha 1 comma alpha 2 belongs to the field F. If such condition is satisfied, then we say W is a subspace. Okay. So if I can show this condition, is satisfied by these two sets, therefore obviously they are going to be subspaces of the respective spaces. How do I show that kernel f is a subspace of V? You take any two elements of kernel f. Okay. So let us take V1 comma V2, be subspaces of base two elements of kernel f. Okay. Then you take what is the meaning of kernel? Elements of kernel will be mapped to zero element. That is the basic property. Do you agree or not? Any
Yes.
element of the kernel is mapping to null element. Now you take so I randomly took two elements. Okay, now I am taking the linear combination. Okay, if I can show that linear combination is also element of the kernel, my work is over. So you take randomly some alpha 1 v1 plus alpha 2 v2. If I can show that this linear combination is also an element of kernel, that means kernel f is going to be a subspace. So when this element will be when this element will belong to kernel f, can you tell me? If this is mapped to null vector, because all elements of kernel should be basically mapping to 0. Any element that is mapped to 0 should belong to the kernel. Am I right? So this is ker and this is image. So that's why you check whether f of alpha 1 v1 plus, okay, f of alpha 1 v1 plus f of alpha 2 v2 is mapping to 0 or not. So what is alpha 1 v1 plus alpha 2 v2? Now can I write it as alpha 1 f of v1 plus alpha 2 f of v2? Can I write like this? Can I write like this or not?
Yes, sir.
Why? Because our f is a linear transformation. Because of the linearity only you are able to write like this. Otherwise you cannot write. So what is f of v1 now? F of 1 is 0. So alpha 1 into 0. And what is f of v2? 0. So alpha 1 into 0 is 0 vector. Alpha 2 into 0 is 0 vector. Basically this is a 0 vector. Therefore f of alpha 1 v1 plus alpha 2 v2 equal to 0 vector means what? Alpha 1 v1 plus alpha 2 v2 also going to be an element of kernel F. Therefore what you can say? Kernel F is a subspace of V. Kernel F is a subspace of V. So if I say dimension of V equal to n, obviously dimension of kernel F is always less than or equal to n, because subspace dimension cannot exceed the original space. Okay, so that is intuitively clear. Is that clear? So in a similar way, how do you show that image F is also a subspace? This image set is also a subspace of this U. You take any two elements. You take any two elements of image, this image set. If the linear combination is also an element of this image set, then that is also subspace. Okay. Now, so what is my aim now? Let us take u1 comma u2 are elements of image of the set F. Image of the set F. Okay. Then how do I show that this is also a vector space? You take u1. You take so because u1 u2 are elements of the image set, u1 u2 will have pre-images. Do you agree? Because you are collecting u1 u2 from the range. Range elements will have pre-images. What are those? v1 and v2. Okay, v1 and v2. So this is v, this is u, this is f. So that means there exists v1 comma v2 belongs to v such that f of u1 is equal to v1. Sorry. F of v1 equal to u1 and f of v2 equal to u2. Now you take linear combination of u1 and u2. What is c1 u1 plus c2 u2? If I want to show that this linear combination is also belonging to image set. Okay, so how do I show that? I want to show that if I can show that this is also an element of image of F, that means this is going to be subspace of subspace of U. How do I show that? You take the corresponding now you take the linear combination of C1 V1 plus C2 V2. You have the scalars, no? You take the scalar, multiply with its pre-image. U1 pre-image is V1, U2 pre-image is V2. Okay, you take a vector of this form. What is f of C1 V1 plus C2 V2? C1 V1 plus C2 V2. this is going to be equal to C1 into f of V1 plus C2 into f of V2. Am I right? And you know, f of input is always belong to the range. This is f of input is nothing but an image. Image must necessarily falling into image of f. But what is f of v1? u1. And what is f of v2? u2. Okay, that means c1 u1 plus c2 u2 is also an element of image of f. So you take any two elements in the image set. You take any elements in the image space. Then the linear combination, I am showing it as an element of the same image set. Therefore, this image set, okay, image of f is actually subspace of u. Therefore, both kernel and image are both kernel and images are subspaces of the v and u respectively. Okay, and not only this, you have one more concept. Okay, if I say dimension of, if I say V is finite dimensional. Let us say V is finite dimensional. That means what? V will have a basis. V has a basis, right? What do you mean by basis? Let us say basis equal to B. Okay, because I am telling it as a basis. Basis will have n elements. E1, let us say E2, and so on. En. These n elements are linearly independent. Span of this basis is going to be the vector space V. That means span B. Span B is equal to the whole space V. What do you mean by span? That means you take any element of V that can be expressed as a linear combination of, okay, these basis vectors alpha 1 E1 plus alpha 2 U2 plus and so on plus alpha n Vn. And so on alpha n Gn. Okay, you can always find a coordinate vectors relative to the basis B, alpha 1, alpha 2, and so on, alpha n, so that we can be expressed as a linear combination. Okay, now if this is the basis, okay, if this is the basis of V, we can show that its image vectors are going to be span the image this image space U. Okay, what I am telling, if so you have V, you have U, you have V, you have U. Okay, there is a basis E1, E2, and so on En, which is spanning the entire set, and this is generating the set V, because this is a basis, and because you have a linear transformation f from V to U, each element of V is going to have an image in U. Okay, so E1 may be associated to f of E1. E2 will be associated to f of E2. That is nothing but the image of the basis element. So obviously En will be associated to f of En. Okay, and you can show that these image elements actually going to span the image. That means what I am trying to say, image of f can be a span of the image of the basis elements f of E1, f of E2, and so on f of En. Image of f is basically a subspace of U. Every subspace, therefore, because it is spanning the entire image space, what can you say about the dimension of the image space? What can you say about the dimension of the image space? Will it be n or less than n? Because this space is generated by n vectors. Can I say that
Yes,
dimension of this space is going to be n? Will it be n or less than n?
Less than n.
It can be n or less than or equal to n, right? You cannot say always equal to n, because when it will be equal to n, if these elements are linearly independent. We know E1, E2, En are linearly independent. That does not mean that their images are also linearly independent. Do you agree? So, yeah, set of elements are spanning the space. Therefore, the space will have dimension less than or equal to n. Okay, less than or equal to n. So when I say less than or equal to n, that means it is finite dimensional. So U may be finite dimensional or infinite dimensional, but image space is always finite dimensional as long as V is a finite dimensional. When V is finite dimensional, image of the space is also dimensional, because V is actually linked with image F, not with U. There is nothing to do with U. This is only really concerned with the image of the elements of V, which is nothing but the image space. Okay, so when V is a finite dimensional space, okay, then kernel of this is also finite dimensional. Its dimension is less than or equal to V, and its image space is also finite dimensional. Is it okay? Is this point clear to you? Okay, shall I proceed?
Yes, sir.
Right. Let us say something like f is a function from, let us say, r power 3 to r power, let us say r power 4 to r power 4 to, let us say, r power 8. It is a linear transformation. Let us say if it is a, I'm telling it as a linear transformation. So what is the dimension of V? What is the dimension of the domain? Can you tell me? R power 4 means
4.
what? 4, right? So dimension of V is 4 here. Okay. And what is dimension of U codomain? 8.
8.
And what will be the so what I am telling, kernel of dimension will be less than or equal to 4, because kernel F is a subspace of V. And I am telling dimension of the image space. What will be the dimension of the image space? What is the maximum value of the dimension of the image space?
8.
No, that is what I am telling. See here, what is n? Dimension of V, no?
Dimension of V, sir.
So dimension of the image space cannot exceed 4. That is what I am telling, right? Codomain can be of any dimensional. That can be infinite dimensional or finite dimensional. But the dimension of the image space will not exceed n. What is n? N is the dimension of the domain. Do you understand this point? E1, E2, E3, E4. What are these images? F of E1, F of E2, F of E3, F of E4. F of E1, F of E2, F of E3, F of E4 generating the image space. That means dimension of the image space cannot be more than 4. 4. That means always less than or equal to 4. Is that point clear?
Yes, sir.
Right. Now once this is clear, now we are ready to prove rank nullity theorem. Rank nullity theorem. So what rank nullity theorem says is that if V is a finite dimensional, let V be a finite dimensional space of dimension n. Let f from V to U be a linear transformation. Okay, and I said I said this is a subspace, right? And this dimension of kernel F is called actually nullity. Kernel F is a subspace. Subspace will have dimension. That dimension is called nullity. Okay. So nullity of F. Okay. Nullity of F is less than or equal to n. And this is also a subspace, I said. Image space is also subspace, I said. Okay. This is also dimension. This dimension is called rank. This dimension is called rank. Okay. So dimension of the image space is called rank. Okay. Dimension of the kernel is called nullity. Then what the rank nullity theorem says is that dimension of V is equal to dimension of null space plus dimension of range space, or you can say image space, range space. Okay. So when I say this is n, if I denote with the rank of the null space with row, and if I say rank dimension of the range space with r, so what it says is n equal to nullity plus rank, or rank plus nullity equal to the dimension of the original space. Okay. So from this, what is nullity formula? Can you say? I will prove the theorem because that theorem is there in your syllabus. Before proving the theorem, let me clarify. What is nullity formula? If I say nullity is rho, so what is sorry, already written, right? So from this, what is rho? Rho is nothing but n minus r, which is nothing but a dimension of null space. What is null space? Set of vectors which are mapping to 0. Okay. Now you see, you are solving the system of linear equations, right? Okay. The how many independent solutions you are getting? Ax equal to 0 has how many independent solutions I said? N minus r linear independent solutions. Do you remember? The set of solutions of a homogeneous system forms a space called solution space, I said. Okay. And that solution space has a dimension. That dimension is n minus r. Why? Because I said A is nothing but a matrix which is acting like a transformation. A is a transformation which I discussed earlier with FA. Okay, you have a dimension, you have a space r power n to r power m, and you are taking x1, x2, and so on xn, which are mapped to 0. This is x. So what is the relation? What is 0? 0 is nothing but image of A at x under the mapping A. So you collect all x which are mapped to 0. You collect all x which are mapped to 0. What is that called? Kernel. Do you agree?
Yes, sir.
And set of, and so I said kernel F is nothing but a subspace of the V. Therefore, that subspace we are calling it as a solution space. Okay, that solution space will have a dimension. What is the dimension? N minus r, which is nothing but the, I said the dimension of the kernel is nothing but nullity. So nullity is nothing but the n minus r. And already you have seen every homogeneous system of equations are having n minus r linearly independent solutions. You remember? Suppose there are n variables. Okay. Suppose Ax equal to 0. Suppose A is a 3 by 5 matrix. Okay, R equal to, let us say, rank 2. rank 3, let us say r equal to rank 3. Then what do you mean by n minus r? What is n here? M by n means what? N equal to 5, r equal to 3. N minus r means what? 5 minus 3 equal to 2. Two independent solutions. That means you can express the solution like this: c1 into x1 plus c2 into x2. Something like c1 into 1 2 0 plus c2 into 2 3 0 2 3, like this. You expressed this kind of solution in this form when you're solving homogeneous system of linear equations. Do you remember?
Yes, sir.
Okay, so they are what are they? They are nothing but the linearly independent solutions which is generating the generating the solution space, which is nothing but the kernel. Okay, kernel is itself is a subspace. Is this clear?
Yes, sir.
Okay, so what rank nullity theorem says, I want to show that dimension is nothing but the dimension of the space V is nothing but the some dimension of the null space and the dimension of the range space. Okay, so how I am going to show this? Okay, listen carefully. May I proceed?
Yes, sir.
Right. So now listen carefully. Okay, very tricky. Listen carefully. Okay, so I have a linear transformation F, which is mapping from a finite dimensional vector space. Remember, it is finite dimensional. U can be finite dimensional or infinite dimensional. I didn't assume anything on U. You observe. I only assumed that V is finite dimension. I didn't say anything about U. Okay. So V is a dimension from F is a linear transformation from a finite dimensional vector space to another vector space U. Okay. So we are having a kernel. We are having a kernel which is a subspace of V. This is ker F. Okay, and we are having a range space which is a subspace of U. This is a image of F. Okay, so dimension of V is n. Okay, so because it is a subspace, okay, and I said it will be finite dimensional. Okay, when V is finite dimensional, range space is always finite dimensional, I said. Therefore this finite dimension will have certain dimension. Okay, let us say that dimension is R. So when I say the dimension is R, that means there is a basis. That means uh, that means there is a there is a basis of this image space. Okay, that basis elements can be like this: U1, U2, and so on, UR. What are these? These are the basis elements of range space. Okay, this is the basis of the range space. Okay, so what I am assuming that, okay, so image space or range space is spanned by span of u1, I'll say like this: span of b, where b equal to u1, u2, and so on, ur. What is this? A basis. Basis means what? It is having two qualities. One is they are linearly independent, and their span is going to be the whole space. Whole space in this case, range space. Basis of, okay, image range space. Okay. Now because this is also a subspace of V, no, when I say this is a subspace, and because V is finite dimensional, ker V is also finite dimensional. Let us say it is a dimension of dimension of image space, I'm assuming it as R. Okay, so I'm assuming that dimension of the ker space equal to, let us say, S. Okay, so when I say dimension is S, that means there are set of elements, okay, which are spanning this linearly independent elements which are spanning this, let us say call this as W1, W2 and so on, WS. Okay, so this W1, W2, WS spanning the kernel space and they are linearly independent. Okay, so that means let me call it as A. Okay, so where A is equal to W1, W2 and so on, WS is a basis of what? Kerf. Okay, so what is my aim now? My aim is to show that n equal to, which is nothing but the rank, and this is nothing but the nullity. So I want to show that n equal to rank plus nullity. That means this is nothing but R plus S. That means I have to show that what is n? Dimension of V equal to n, which is nothing but R plus S. I should show. That means V will have a dimension n, no? That means what? If I can generate R plus S linearly independent sets, linearly independent elements which generate the whole space, then that means to say that it is of dimension n. Okay, so that means to show that. Okay, so therefore it is sufficient to show that it is sufficient. I consider A and B, right? It is sufficient to show that it is sufficient to show that V has R plus S linearly independent elements that spans V. If I can show that R plus S elements are linearly independent, if they are spanning V, then R plus elements forms a basis. And you know any two bases will have same number of elements. Therefore, R plus S must be equal to N. Is this clear? Okay. If I can find a basis of V which is containing R plus S elements, then R plus S has to be N, because any two bases of V are going to be have same number of elements. We know basis of V is containing N elements because dimension of V is N. Therefore, because R plus elements of S forming a basis, then R plus has to be equal to N. Is that point clear to all of you? May I proceed?
Yes, sir.
Right. Now, you take these elements u1, u2 and so on, u1. Where are these? These are the elements of range, right? Every element of range will have a pre-image. Do you agree or not? u1 will have a pre-image, u2 will have a pre-image, ur will have a pre-image. Am I right? So assume that they are v1, v2 and so on, vr. Okay. So since u1, u2 and so on, ur belongs to kernel of f, okay, there exist v1, v2 and so on, vr belongs to the set V such that v1 is mapped to u1, v2 is mapped to u2 and so on, vr is mapped to ur. vr is mapped to ur. Do you agree? Okay, if that is the case, now first I am going to show this part. I'm going to show this part first. Okay, I'm going to show this part first. Okay, so for that what I'm going to do, right, so I'm going to show that a set C. Okay, we will show that okay, v1 v2 and so on vr, and what are the basis elements of kernel? w1 w2 and so on ws, no?
Yes, sir.
Okay, so what are those? w1 w2 and so on ws. We will show that this is a basis of v. If I can show that this set is a basis of v, how many elements are there in this basis? R elements plus S elements means R plus S. And dimension of v is n, means R plus S has to be n. Is that clear to you?
Yes, sir.
Now, if I want to show that this is a basis of v, I have to show two things. Span of this, okay, is going to be the entire space, and all these elements are linearly independent. So first part I'm going to show. How do you show that span of this is the entire space? You take any element, randomly selected element of V. If I can show that any element of V can be expressed as a linear combination of elements of this, that means to say that the all possible linear combinations are nothing but the entire space. Is that clear? So what is the first part? Let me call it as a set. Let us say set C. Let us say for the time being, let us say set C. Okay, so what is the first part? To show that span of C is the entire space V. For that, what I am going to do, you take any randomly selected element of V. If I can show that V can be expressed as a linear combination of the elements of this R plus elements of C, that means that C is spanning the entire set. Okay, so when I say V, so I'm going to draw the diagram again. So V to U, you have a mapping F. I'm selecting a element of V randomly. So when I'm selecting an element randomly, it will have an image that will form into range space. Okay, so that means what? F of V belongs to range space. Okay, F of V belongs to range space or image of F. And you know, image space of F is nothing. Image space has dimension. Okay, what are the dimension? Which one is generating this space? W1, W2, WR. Do you remember?
Kernel.
Did you see this? This image space is generated by U1, U2, and so on UR. That means generated by means what? Any element of this image space can be written as a linear combination of elements of U1, U2, and so on UR, because this is the basis. Okay, so this is the basis. This is the basis of kernel. And what is this? This is the basis of image F. Image F. Okay. So because okay, which is nothing but the spanning of, okay, which is nothing but the span of U1, U2, and so on UR. You know, because U1, U2, you are forming this basis. Therefore, there exists some scalars alpha 1, alpha 2, and so on alpha r, such that f of e can be expressed as a linear combination of these elements. Okay, that means f of v can be expressed as, okay, alpha 1 u1 plus alpha 2 u2 plus and so on plus alpha r u r for some scalars. For some scalars. For some scalars, alpha 1, alpha 2, and so on, alpha. Okay. Now you define. Okay. Now you define. Okay. Okay. Now you define a vector like this. Okay. Now you define vector v dash as like this. Okay. What is the pre-image of u1? Can you tell me? What is the pre-image of u1? What is the pre-image of u1? v1.
V1.
Pre-image of u2 is v2, right? So you define a vector v dash like this. Okay. Alpha 1 into, you take the pre-image of u1. What is that? v1. Alpha 2 into, you take the pre-image of v2, u2, which is v2, and so on, plus alpha r into, you take the pre-image of ur, which is vr, minus v. What is v? V is nothing but our general vector v. So you are forming a vector. Difference of two vectors is a vector. Where is this v dash belonging to? Is this v dash belonging to v or u?
V, sir.
V, because v1, v2, vr are elements of v. The linear combination is also elements of v. V is also an element of v. So element of v minus element of v is also an element of v. Okay. So what is f of v dash? Now what is f of v dash? Apply f. F of alpha 1 v1 plus alpha 2 v2 and so on plus alpha r vr minus v. And I know f is a linear transformation. I can write it as f of alpha 1 v1 plus alpha 2 v2 plus and so on plus alpha r vr minus f of 2. Okay. Now what is f of alpha 1 v1? I can write it as alpha 1 into f of v1 plus alpha 2 into f of v2 plus and so on plus alpha r into f of vr minus f of v. Now what is f of v1? F of v1 is nothing but u1. F of v2 is nothing but u2. Do you agree? Am I right or no? So alpha 1 alpha 1 u1 plus alpha 2 u2 plus and so on plus alpha r ur minus f of v. Now can you identify what is alpha 1 u1 plus alpha 2 u2 plus alpha r ur? See, alpha 1 u1 plus alpha 2 u2 plus and so on alpha ur. What is it? That is nothing but f of v. So f of v minus f of v. What is f of v minus f of v? 0. So what you are getting is f of v dash is going to be 0. So v dash belongs to where? Whenever an element is mapped to 0, that element belongs to what set? The set of elements which are mapped to the null element belong to what space?
Nullity.
Null space. That means v dash is an element of kernel. Okay. And this kernel f is a subspace. When I say subspace, it has a basis. That means this can be generated by a span of w1, w2 and so on, ws. Am I right? Because I said dimension of this nullity. Dimension of this nullity is yes. This is the basis of the kernel. So any element in this kernel can be expressed as a linear combination of these elements. Okay, because this element is an element of kernel F, this can be written as a linear combination of elements of W1, W2 and so on. That means V dash can be expressed as some D1 W1 plus D2 W2 plus and so on plus ds ws for some scalars d1 d2 and so on dn. But what is V dash? You see, V dash is nothing but this expression. So what is V dash? V dash means alpha 1 v1 plus alpha 2 v2 and so on plus alpha r vr minus v is equal to d1 w1 plus d2 w2 plus and so on plus ds ws. So from this, what is v? Take these terms to left hand side. So what is v? V is nothing but alpha 1 v1 plus alpha 2 v2 plus and so on plus alpha r vr minus d1 w1 plus minus d2 w2 and so on minus ds ws. That means what? We are able to express v, okay, is a linear combination of what elements? v1 v2 and so on vr and w1 w2 and so on ws. That means what? This is nothing but elements of C. Therefore, you are able to express this is a randomly selected element V. Any randomly selected element you are able to express as a linear combination of only these set of elements V1, V2, Vr and W1, W2, Ws. That means what? V equal to span of the entire set, the entire subspace, the entire dimensional space. V equal to span of V1, V2 and so on Vr, W1, W2 and so on Ws, which is nothing but span of C, where C is equal to the set of vectors V1, V2 and so on Vr, W1, W2 and so on Ws. Can you see how I defined C? C is nothing but C is nothing but V1, V2, Vr, W1, W2, Ws. V1, V2, Vr and W1, W2, Ws. So we are able to show that this set is spanning the entire space V. So if I can show that this set is linearly independent, then that means this is a basis of V. Therefore, basis has n elements. Therefore, r plus elements has to be equal to n. Is the first part of the proof is clear to you? All of you understood this? Shall I proceed? So where is the trick? The trick lies here. We formed a vector like this, V dash equal to, okay, linear combination of a set of vectors minus V. What are the set of vectors? Pre-images of U1, U2 and UR. Okay, what are U1, U2, UR? They are the, I think there is a mistake here. They are not W1. They are U1, U2. Okay, so they are the pre-images of U1, U2 and so on UR. V1, V2, Vr are the pre-images of U1, U2, UR. What are U1, U2, UR? UR are the basis elements of range space. V1, V2 are the pre-images. Okay. And what are W1, W2, Ws? W1, W2, Ws are the basis elements of kernel F. Okay. So basis elements of kernel and pre-images of basis elements of image is going to be form the entire V dimensional space. Shall I proceed? What is the next part of the proof? To show that C is linearly independent. C is linearly independent set. Am I clear till this part or not? Did you understand what we have discussed so far?
Yes, sir.
Yeah. So how do you show that set of vectors are linearly independent? Consider C1 V1 plus C2 V2 plus and so on. Not C1 V1. Let us say X1 X1 X2 and so on. Okay. Consider a linear combination of these vectors. What is a linear combination? X1 V1 plus X2 V2 and so on plus XR VR plus let us say Y1 W1 plus Y2 W2 plus and so on plus YS WS. Consider this linear combination is 0. What is the meaning of linear independent set? Whenever this linear combination is 0, if I can show that that is possible only for all these scalars 0. That is, this linear combination is 0 only when I take x1 0, x2 0, xr 0, y1 0, y2 0 and so on ys 0. If I can show that this is possible only when all the scalars are zeros, that means to show that C is linearly independent set. Okay, so you consider you apply f on both sides. If I am considering this linear combination is 0, okay, if I am considering this linear combination is 0, you apply f on both sides. Okay, so what is f of this? F of x1 v1 plus x2 v2 and so on plus xr vr plus y1 w1 plus and so on plus ys ws must be equal to f of 0. And you know f is a linear operator. That means what? X1 into f of v1 plus x2 into f of v2 plus and so on plus xr into f of vr plus y1 into f of w1 plus y2 into f of w2 plus and so on plus ys into f of ws must be equal to what? Can you tell me what is this value? F of 0. What will be f of 0? What is f of 0? Can you see this? 0 is always mapped to 0, right? Are you seeing this or not? Please respond. Hello.
Yes, sir.
So now I can write f of 0 equal to, now I can write f of 0 equal to 0. F of 0 equal to 0. Now in this expression, can you reduce the number of terms here? What is f of w1? Can you tell me? Where is w1? W1, W2, Ws. Where are these elements? These elements are belonging to kernel f, and any element in the kernel f will be mapped to 0 only, right?
Yes, sir.
Therefore, I can reduce these elements. So I know that f of w1, f of w2 and so on, f of ws is going to be 0. So that means to say that x1 into f of v1 plus x2 into f of v2 plus and so on plus xr into f of vr only you have, because remaining terms are going to be 0. But what is f of v1? U1. And what is f of v2? U2. And so on. What is f of vr? UR. And what are U1, U2, UR? What are U1, U2, UR? basis. U1, U2 are basis of images. What is the property of basis? Basis is nothing but linearly independent set. So because U1, U2, UR are linearly independent, a linear combination of linearly independent set equal to 0 means what? Which one has to be 0? X1 has to be 0. X2 has to be 0. So X1 has to be 0. X2 has to be 0. And so on. XR has to be 0. So these elements are already 0. Okay. What is the original expression? Original expression is this. In this we already concluded that x1 0, x2 0 and so on xr 0. How many elements are remaining now from this equation? Therefore you call this as some star, because x1 x2 xr are 0. So that means star implies what is remaining is y1 w1 plus y2 w2 plus and so on plus ys ws equal to 0. But you know W1, W2, Ws are linearly independent set, because W1, W2, Ws forming the basis for the
Kernel.
kernel F. Okay, so these are all the forming the basis for the kernel F. Therefore, basis means they are linearly independent. When they are linearly independent, linear combination of linearly independent vectors 0 means y1 has to be 0, y2 has to be 0 and so on, ys has to be 0. Therefore, we have shown that linear combination is 0 means, okay, x1 0, x2 0 and so on, xr 0, y1 0, y2 0 and so on, ys 0. That means to say that that means to say that v1, v2 and so on, vr, comma w1, w2 and so on, ws forms a linearly independent set. Call this as C. So C is linearly independent and span of C is equal to set of V, means basis of V equal to C. Okay, that means C has n elements, but we know C has how many elements? R plus S elements. Okay, so this implies that C has therefore R n equal to R plus S, because any two bases are having the same number of elements. Therefore, what we have proved is dimension of the vector space is equal to rank plus nullity. Did you understand?
Yes, sir.
Now, do you understand why we discussed? We started the discussion from field, vector space, linearly independence, span, everything, right? So just like that rank nullity theorem, you cannot understand. You need to know the notion of linear transformation, dimension, properties, and so on. Is it okay?
Yes, sir.
Right. So we'll one second. So we'll see how to find out rank space and null space, and I will stop the class. So I'll come back to this one. Okay. So I'll just see the summary. So initially have shown what is a function, and how a function can be viewed as how a matrix can be viewed as a function fa. Okay, fa can be viewed as a. Okay, we frequently denote the mapping fa denoted by the letter a. A is nothing but the matrix. Okay, fa of u equal to au. And linear transformation are having these two properties. Okay, f of sum equal to sum of images, f of k into v equal to k into a. Okay, and combining these two, you can put the condition like this: f of linear combination equal to linear combination of images. Okay, generally a linear mapping from R power n to R power m, some others call this kind of linear mapping as linear transformation, and there are some examples given here for linear transformations. This is called projection mapping. Okay, This is called projection mapping. So what is that projection mapping? You have a point. You have a point. Project this point on the xy plane. If you have a point xyz, what is the projection of the point on on the xy plane? Projection means which one we are decreasing? Z. So xyz will be mapped to xy0, exactly down. Okay, so this is called a projection mapping. You can show that projection mapping is a linear transformation. Similarly, translation mapping is a this cannot be a linear transformation because f of g of 0 is not equal to 0. That is what I said. The basic property of a linear transformation is 0 must be mapped to 0. So because 0 is see, x is shifted to x plus 1, y is shifted to y plus 2. So this is a translation mapping. Okay, this translation mapping cannot be called as a transformation or a linear transformation because 0 is not mapped to 0. When you substitute 0, 0 plus 1 is 1, 0 plus 2 is 2. So 1 comma 2 is cannot be 0. Therefore, this is not a linear. Okay, so and matrices can be viewed as a linear maps. That's what I said. Okay, every matrix can be viewed as a vector. And after that, I have shown, and this is the projection mapping. See, A, B, C, its projection is A, B, 0. Okay, so that is what it is shown. Okay, and okay. Rank nullity. See this problem. Okay, let f is a function from r cubed r power 4 to r cubed by a linear mapping defined by like this: f of x y z equal to x plus y minus z plus t, 2x minus 2y plus 3z plus 4t, 3x minus 3y plus 4z plus 5t. Question is, find a basis and dimension for the image of f. Okay, image of f means what? Range space. Okay, so how do you find out the range space? I said range space is generated by f of e1, f of e2, and so on, f of en. What are e1, e2, en? E1, e2, en are the basis elements of v. Okay, and because this is a four-dimensional space, what is the basis elements of this four-dimensional space? 1 0 0 0 0 0 1 0 0 0 1 0 0 0 1. Call this as e1, e2, e3, e4. So when e1, e2, e3, e4 are basis elements of r power 4, their images are going to span the range space. That means f of e1, f of e2, f of e3, f of e4 going to span this entire space, range space. So that's why I computed we computed the image elements. What is the image of 1 0 0 under this mapping? Substitute x equal to 1 here, y equal to 0, z equal to 0, t equal to 0. So 1 0 0 is this one. Okay, 1. Okay, and again substitute these points here, you will get 2. Again substitute these points here, you will get 3. Is it okay? Similarly, substitute these 4 points in these 3, you will get another point. Substitute these 4 points in this, you will get another point. Substitute these points in this, you will get this. So these 4 vectors are going to span the image space. Okay, now we want to, if you want to find out the space generated by these vectors, if you want to find out the dimension of the space generated by this vector, I said earlier, you put them as rows, convert into echelon matrix, count the number of non-zero rows, that is going to be the space generated by the given set of vectors. And we know this is the space generated by these vectors are nothing but range space, and the dimension of the range space is the number of non-zero rows in the echelon form. So how many non-zero rows you are seeing?
2.
Therefore, what is the dimension of the range space?
2.
Now, can you tell me what will be the dimension of the null space? Null space. Now you can use rank nullity theorem, no?
Yes.
So according to that, then what will be the nullity? What should be the nullity? So from this, we are able to identify that. Here. From this, we are able to identify that r equals to n. Sorry, r equal to how many non-zero rows? 2. And what is n? What is the dimension? Dimension of v equal to n. What is n here? 4 dimension. And we know rank n equal to rank plus nullity plus rank. Therefore, nullity equal to what?
2.
n minus r. That means 4 minus 2 equal to 2. So we should get that dimension of the null space must be 0. the dimension of the null space to be 2. Okay, and what are the basis elements of this range space? Means 1 2 3 is one element, 0 1 1 1 is another element. See, these two are generating the range space. These two are generating the range space. Okay, now if you're asked to find out a basis and dimension of the kernel f, what do you mean by kernel f? The set of elements which are mapping to 0. That means I should find all elements which are mapped to whose images are equal to 0. That means I have to find v such that f of equal to 0. F of equal to 0 means what? What is v? X, y, z, t, input function, input point. So what is f of v? F of v is this is defined like this. See, this is f of v. Okay, so this must be equal to 0. What do you mean by 0? 0 is an element of RQ. That means it has 3 dimensions. Okay, so equate image to 0. That means equate the corresponding elements. That means x plus x minus y plus z plus t equal to 0, 2x minus 2y plus 3z plus 4t equal to 0, and 3x minus 3y plus 4z plus 5t equal to 0. What is this called? Homogeneous system. Am I right? And you know how
Yes.
to solve a homogeneous system? This is you write down the coefficient matrix, convert into echelon form, find out the rank, and that means the number of equations are reduced. How many independent variables will be there? N minus are independent variables. See here. So you can show that it is going to have 2 independent solutions. That 2 is nothing but n minus r. So what is the dimension means? That is let us quickly solve here. What is how do you solve this? This is in the form ax equal to 0, right? What is the coefficient matrix? A equal to
1
1
minus.
minus 1 1 1, 2 minus 2, 3 4, 3 minus 3, 4 5. Okay, you convert this into echelon form. Okay, you convert this into echelon. Please convert into echelon form now. Let me copy this 1 minus 1 1 1. So ax equal to, let us say 0, a equal to 1 1, 1 minus 1 1 1, 2 minus 2 3 4, 2 minus 2 3 4, 3 minus 3, 3 minus 3, 4 5. Okay, now how do you convert into echelon form? You apply row operations. R2 gets R2 minus 2R1, R3 gets R3 minus 3R1, and this is equivalent to 1 minus 1 1 1, 2 minus 2 0, minus 2 plus 2 0. Am I right?
Yes, sir.
And 3 minus 2 1, 4 minus 2 2, R3 minus 3R1, 3 minus 3 0, minus 3 plus 3 0, and 4 minus 3 1, 5 minus 3 2. Okay, and now when I say R3 gets now next pivot is 1. So when I say R3 gets R3 minus R2, then this is equivalent to 1 minus 1 1 1, 0 0 1 2, 0 0 0 0. Okay, so so ax equal to 0 means what? Ax equal to 0 means call this as b. So this is equivalent to saying that bx equal to 0. That means to say that, okay, this into xyz t. What are the variables used here? Xyz t. Okay, that means to say that x minus y plus z plus t equal to 0, z plus 2t equal to 0. Okay, so what is the dimension? Dimension of a equal to dimension of rank of a equal to rank of b equal to 2. So what is the order here? 3 by 4. So it will have 4 minus 2 equal to 2 independent solutions. What are the free variables here? Can you see? So when z plus 2t equal to 0, what is z? Minus 2t. So can you identify the independent variables now?
X, Y, T.
T is one independent variable. Can you say you can assign any variable to any value to t? And can z be independent? Z cannot be independent, right? Because z is depending on t. So one of the free variable is t. What is other free variable? One of these two.
X or Y.
X or y, right? So if I consider t as c1 and let us say y as c2, then what you are getting? Z equal to minus 2c1. Okay, and x equal to what? Y minus z minus t. Y minus z minus t. What is y? I'm considering y as c2. What is z? Z is nothing but minus 2c1. What is the t? T is nothing but c1. So this is nothing but c2 minus 3c1. Now you got all the things. Therefore, x, y, z, t. Okay, is nothing but I'll write in the next slide. Okay, so x, y, z, t is any element of r power 4. You can see. Not any element of r power 4, it is element of kernel, because this is mapped to 0, right? So kernel of f, okay, is equal to what is x? What is x? c2 minus 3c1, or I can say minus 3c1 plus c2. What is y? Y is c2.
C2.
What is z?
Minus 2C1.
Minus 2c1. Minus 2c1. What is t? c1.
C1.
Now how can I write this as a linear combination of two vectors? Minus 3 into minus, sorry, not minus 3, c1 into what is this one? Minus 3. There is no c1, I can call it as 0. So minus 2, 1 plus c2 into 1, 1, 0, 0. Is that okay? So it is in the form c1 w1 plus c2 w2. So what is the basis? What is the basis of that? Means you are able to express any element of kernel as a linear combination of two vectors. What kind of vectors? Two linearly independent vectors. Therefore, okay, this spans. Okay, these two vectors alone, these two linearly independent vectors spans kernel f, means these two forms a basis. Okay, therefore basis of kerf is, okay, minus 3, 0, minus 2, 1, comma, what is the next vector? 1, 1, 0, 0. Therefore, what is the dimension? Dimension of kerf is rho equal to 2, number of elements in the basis element. Is it clear?
Yes, sir.
So this is how we can find out okay, images. You can find out the basis and dimension of image, basis and dimension of the range space, basis and dimension of the kernel space. Okay, so I will conclude.